knowing what they look like. So on the front here, I have the 4 parent graphs, the 2 log graph, the basic log graph with any base of b, and the natural log graph, which obviously has a base of e. And you always have 2 critical points and a critical asymptote, or an asymptote. So with log functions, your asymptote's the y-axis. Both have a critical point at 1, 0, and then your second critical point is at the base comma 1, which in the case of the natural log is e comma 1. So they're pretty much the same thing, just they have a different base, and you know, all of these are going to have a different base anyway, so it's the base comma 1. Whereas the exponential parent graph, instead of base comma 1, it's 1 comma base. And instead of 1, 0, it's 0, 1. And instead of the y-axis being the asymptote, it's the x-axis being the asymptote because they're inverse functions. So all things x and y are flip-flops. So when I wanted you to get some practice with graphing these and sketching a graph of each of these and being sure that you know where the critical points and asymptotes are. Okay? So every one of these is some sort of transformation. So, and you're not going to be able to fit all 10 of these on the same one, but we'll start with number 1, and we can just sketch a quick graph. And this is our natural log parent graph shifted up 2 units. So very lightly, your parent graph is going to have 1, 0. E is approximately what number? Do you know? 2.7. So approximately 2.7 comma 1. And then very lightly, because this isn't my actual graph, there's your parent graph. And when you add 2 at the end of a function, how does it move it? Up 2 units. So it's a vertical shift up 2 units. So this critical point is going to move up 2 units, and that's going to be at 1, 2. This critical point is going to move up 2 units, so that's going to be what? What are the coordinates of that now? What'd you say? E3, good. And then your vertical asymptote, which was the y-axis, gets shifted up 2 units. What happens to that? When you shift a vertical line up 2 units, where does it? Still the same thing. So here is the graph of this function. You can kind of get rid of your guide there. So your asymptote, and I want you to label all that, your asymptote is still x equals 0. So that's number 1. Make sense? Okay. So number 2, again, I'm going to start with the parent graph just to sketch. What's my base? What's the base of the exponent here? 3. Not the negative. The negative's not being raised to the exponent, just the 3. So the 3 to the x power exponential parent graph is 0, 1, and then 1, 1, 2, 3. So it's going to look like this. That's the parent graph of 3 to the x power. Which transformation do we address first, the negative or the plus 2? The plus 2, you work from the inside out. So how does the plus 2 shake things up here, Maggie? No, up 2 is if the plus 2 is after the function, after the parent graph. This is within the graph, within the exponent. Over to which way, left or right? Left, because everything horizontal is backwards. So we're going to first move every point left 2, every point, every asymptote, and then what does a negative out in front do? flips it vertically over the x-axis. So I'm going to take this point, move it left 2, and then flip it over the x-axis. So it's 3 above, I'm going to go 3 below. So that just became -1, -3. The 0, 1 is going to be moved left 2 and then flipped over. So that just became -2, -1. And then my asymptote, which was the x-axis, got moved left 2, which doesn't change it at all, right? And then flipped over the x-axis, which means flipped over itself, which doesn't change it at all. So your asymptote is still the same, your horizontal one, and then your graph looks like that. And I'll label my asymptote y equals 0. And I'll get rid of my guide there. Any questions on that? I would like to jump to number 8. Yeah, 8. At least you have one. Okay. Number 8 is an exponential function with a base of e. So your parent graph initially is going to have a 0, 1, and then in a 1, comma e, so 1, comma 2.7, and an x-axis asymptote. Good? And what transformations happened here? And in what order? Right 8. Right 2 and up 3. So my point needs to move right 2 and up 1, 2, 3. Which, what are now the coordinates of that? It was 1, comma e. Now it's 1, 2, 3, comma e plus 3, right? Does that make sense? So it was at e, but I moved that up 3, and so since e is an irrational number, we'll keep it in terms of e and call it e plus 3. So the x-coordinate is 3. And the y-coordinate is e plus 3 because of the shift up. On this one here, we are going to shift it right 2 and up 3, which should be easier. Here you go, guys. And that point is 2, comma 1, 2, 3, 4, 2, 4. And my asymptote, which was the x-axis, got shifted right 2 units, so just move it right 2 units, which doesn't change it, but then up 3, 1, 2, 3. So your new asymptote is right here. So I'm going to get rid of my old point, my kind of parent graph, and then just come down and approach the asymptote, making sure I don't cross the asymptote, and the asymptote is now y equals 3. So we did 1, 2, and 8. And then I would like to do, you can do number 3. Okay? So starting with a log parent graph with a base of 4. Log parent graphs definitely have 0, 1, and they go through, or go up to the, go up to the y-axis as an asymptote. And because the base was 4, my next point is 4, 1. So 1, 2, 3, 4, 1. And this again, this is just a parent graph, so lightly we'll eventually erase that. But what are the transformations and in what order to convert log base 4 of x to log base 4 of 2x minus 3? What transformations and in what order? Paul. Which, first of all, horizontally or vertically? When it's within the parent function, it's horizontal. And by within the parent function, I mean it's log base b of x. So anything that's within here is horizontal. Anything that's out in front or after the fact is vertical. Is that clear? Okay? And anything that happens horizontally is kind of the reverse of what your instinct would tell you. Your instinct would tell you if you're multiplying by 2, you're probably stretching it, right? But the opposite is actually true when you're dealing with horizontal movement. So this is actually a horizontal compression of a half, followed by, try this one, Paul. What's the minus 3 do? Shifts it down 3. So we're going to horizontally compress this graph inward towards the y-axis and then shift it down 3. So starting with this point, compressed in a half is going to put it there, and then down 3 is going to put it right. I'm going to erase this while I can and keep the remnants underneath. So shift it in by a half and down 3, and the point there is 1/2, comma, negative 3. This point that was at 4, 1 gets compressed in to 2. That's your horizontal compression by a factor of a half, and then shifted down 3. 1, 2, 3. So this point is at 2, negative 2. And your vertical asymptote, horizontally compressed, still the same thing. Stretches and compressions don't touch our asymptotes at all. Shifting can and cannot, it depends. This one's shifting a vertical line down 3. So if I take a vertical line and shift it down 3 units, it's still the same vertical line. So that asymptote has not moved, and my graph for this function looks like that, making sure we're approaching our asymptote, never crossing it. And label your asymptote, x equals 0. So always have 2 critical points and the asymptote label. Any questions on that? Okay. So for those of you who came in a little late, I was recording that, so I'll put that on the web page so that you have it. And for the couple examples that you missed, and the introductory explanation. Then take out your review packet. And I might as well just keep recording all this too, right? Okay. Questions? Jenna. 63. The minimum value of the derivative occurs when? The minimum value of the derivative. So that's an interesting twist, because normally they would ask you the minimum value of the function. Oh. Yeah, what did you do? Right. Right. So as soon as I kind of said that phrase, you picked up on it, right? Because the minimum value of the function is what we would use the first derivative to find. So if I did f prime of x, and I got 15x to the fourth plus 20x cubed, and then I found the zeros and the undefines of that, factor out an x cubed, 5x cubed actually, and I'm left with 3x plus 4. I have a 0 at 0 and at negative 4/3. So if I plug in a 1, my derivative is positive. If I plug in a negative 1, I get 15 minus 20, so my derivative is negative. If I plug in a negative 2, I get a positive, right? It's negative 2 to the 4. 2 times 4 is 16. 16 times 15 plus 20 times negative 8. So that's minus 160, and 15 times 16 is bigger than 160, so that'll be a positive. So what I just found is that on my function, I'm increasing and then decreasing and then increasing again. So I have at least a relative minimum on my function at 0. Okay? But that's not, first and foremost, that's not, obviously this graph, that's just a relative minimum. It's not going to be the absolute minimum, right? This is a positive odd behavior. So it's going to go down forever and then kind of increase forever overall. But I've got a relative max and a relative min. This question asks for the overall minimum value of the derivative. This is giving me that I have a relative min on my actual original function, not the minimum on my derivative. So if I want the minimum of my derivative, I need to find the second derivative and do the same thing. Essentially, a minimum of your derivative is going to be a point of concavity. Okay, it's a minimum of the derivative, not a minimum of the function. So my f double prime of x will be 60x cubed plus 60x squared. Factor out 60x squared, I'm left with x plus 1. And so I have critical points at 0 and at negative 1. Okay, so if I plug in a 1, I get a positive times a positive. If I plug in a negative 2, I get a positive times a negative, which is a negative. And if I plug in a negative 1/2, I'm going to get a positive times a positive, which is also a positive. So my minimum of my derivative, which is where this second derivative decreases, then increases, and continues to increase. So the minimum of my derivative is at negative 1. That's a tricky one. You got to pay attention, because it's easy to read that and just not really process the difference in questioning there. You see minimum, it really normally reads the minimum value of the function occurs at. And then when you see the minimum value of the derivative, now that's suggesting we have to go all the way to the second derivative. So just be careful in your reading. Don't go too quickly. Next, that was what? 53? Okay. Dylan? 50. How many points of inflection? Okay, points of inflection are second derivative questions, and where the concavity changes. So what did you get for your first derivative? Okay. And what did you get for your second derivative? Good. And what did you get when you factored that to find your critical points, or what did you get for your critical points? Positive 3/8. Is that your mistake? Did you have positive 3/8? You had negative 3/8? So it was probably your mistake. Yeah, but they're not both necessarily points of inflection. They're both critical points. They're both possible points of inflection. Just like in the first derivative, things are possible maxes and mins, but there has to be a change from increasing to decreasing. There has to be a change from concave up to concave down. And if there's not, if we get something like this being the second derivative, this was concave down, concave up, concave up. So the only point of inflection here was -1. And we are probably going to find the same thing here, and I'm getting that from the fact that we're squaring this. Usually the point in time when you get something like that, same thing here. Because that was a squared root, the behavior is the same on either side, typically. Okay? Just like if it's a squared asymptote, the behavior is the same on either side. So if I plug in -1, I'm going to get a positive times a negative. If I plug in a fourth, I'm still going to get a positive times a negative. And so 0 is not a point of inflection. And then if I plug in +1, I'm going to get a positive times a positive is a positive. So the only point of inflection occurs at 3/8. So the answer was 1. Emily? Find the approximate value of C on the closed interval from 0 to 2 that satisfies the mean value theorem. So f of x is sine of x squared. And the, is this a calculator question? Just look at your answers. All right, we'll use one just for the sake. But don't worry, it won't happen on your final. I've checked. But just for the sake of reviewing the mean value theorem, and we're talking from the interval from 0 to 2. The mean value theorem means we're looking for the point on this curve that has the same instantaneous slope as the average slope from start to finish on the interval. So the sine of 0 squared when you plug it in is 0. And the sine of 2 squared when you plug it in, I gotta go back to radians. Sine of 4 is -0.7568. So my average rate of change, my average slope is y2 minus y1, -0.7568 minus 0, over 2 minus 0, which will be -0.3784. So that's my average rate of change. That's what I need to set my derivative equal to. What's the derivative of sine? Cosine. So cosine of x squared times the derivative of what's inside, which is 2x. So I want to know when this equals -0.3784. And that's where, again, your calculator is going to have to come in. So I would... What? Did you just miss my conversation that I had 5 seconds ago? Oh my gosh. Somebody help her. Daniel, you're not listening. As soon as I saw this, I looked at the answers and I go, ooh, this is a calculator question. We're going to do it to practice the mean value theorem concept, but don't worry, this won't happen on your final. Children, is that what I said? Does that answer all the questions you just repeated? Yeah. Dylan hates me, that's why. I'm just kidding. Cosine of, well, maybe I'm not, I don't know. Cosine of x squared times 2x is one side of the equation, and negative 0.3784 is the other. I'm going to make my window from negative 5 to 5 and negative 5 to 5. Ooh, gross. I'm just looking between 0 and 2, right? That makes my life easier. So if I'm just looking between 0 and 2, let me do this. So right here. So second trace, option 5, intersect, get over there, enter, 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 1.3099 B. That's clear. So that's B. So essentially what that's telling us is that if I take this graph, just to, again, give you some visual backup here. If I take this graph and look at it from 0 to 2 only, the average rate of change, I'm going to change my window because this is all wasted space right here. I'm just going to go on my y-axis from negative 2 to 2. Okay, my average rate of change is from here to here, kind of that slope there. So where on the graph is this going to be a tangent? And it's right there at approximately that value 1.3099 is right about there. Okie doke. Any questions on that? Okay. Sorry about that. Calculator one. Other questions? Daniel? You may. I feel like that's classic teaching. That anything else? No. Well, tomorrow. Well, we still have one person that needs to do their corrections. So if I'm not here tomorrow, you can grab them yourself. They're going to be right here. I don't know.
I better remember where you looked up.
Emily. What number? We did? No, we didn't do 54. Minimum, so we're back to what is the minimum value of the function? So this is just a first derivative question, but this is on the closed interval. So when you're looking for the minimum value on a closed interval, which is different than the minimum value on an open interval. First of all, because this is positive odd, this wouldn't have an overall minimum value. It wouldn't exist, right? Because it goes towards negative infinity. But when you're dealing with the closed interval, like between negative 2 and 5, and you're only looking at a certain portion of the graph, there is a minimum value. You just have to find it. And this is where we list out our critical points. And the critical points, first and foremost, have to include those endpoints. Negative 2 comma something, 5 comma something. Your other critical points are going to come from where the derivative, of course, equals 0 or is undefined. This one is not going to be undefined, but it will equal 0. I will factor out a 3. And it will equal 0 at 3 or at negative 1. And then you plug each one of those into your original and then pick the minimum value. And they're asking here, sometimes they might say, where does the minimum value occur? If they ask you where it is occurring, they're asking you for the x-coordinate. If they say what is the minimum value, they're looking for the y coordinate. So negative 2 cubed is negative 8, minus 3 times 4 is minus 12, plus 18 plus 1, what's that? Negative 20 plus 19, what? Negative 1. Plug in 5, you're going to get 125, minus 3 times 25, so minus 75, minus 45 plus 1. 6. Come on. When you plug 3 into your original, you get 27, minus 3 times 9 is minus 27, minus 9 times 3 is 27, plus 1 gives you negative 26. And when you plug in negative 1, you get negative 1, minus 3, plus 9, plus 1, that's 10 minus 4 is 6. So your minimum value is negative 26. Next. You did well on the related rates one, huh? Good. That's it? We're good? Okay. No. I can show you what your final grade is. Okay. So your homework tonight is just to finish the back of that, well, the problems on that worksheet. Get a separate sheet of graph paper to sketch these things out.